Hi everyone, my name is Hebah, and today I'm going to be talking to you about magnetism and superconducting circuits. So specifically, we're going to go on a little dive in magnon and photon coupling. So I thought it was really interesting. So I guess we're going to work to understand like this device by the end of this presentation. This image shows two magnons remotely coupled, assisted by superconducting circuits. So we're first going to talk about like magnons. I think some people have already talked about it in the presentation, but we'll just do a little refresher. What are superconducting circuits? How do we couple magnons to superconducting circuits? Some implementations of devices, and then like future directions of this field. Yeah. So the first thing is, what are magnons? Magnons are elementary quasi-particles of spin waves. And so you can generally think of them as the collective excitation of electron spin structures in crystal lattices. And you treat them quantum mechanically as a Heisenberg ferromagnet, or that's kind of one of the more simpler models. So at 0 Kelvin, this object has perfect magnetization. And then as your temperature increases, you see spontaneous magnetization of your different spins, which gives us our quantized spin wave. So superconducting circuits come from circuit quantum electrodynamics, which is where you use LC circuit models to kind of describe photon modes in superconducting resonators. And so this comes from cavity quantum electrodynamics. Cavity quantum electrodynamics is a very well understood field in physics, where we can kind of describe how atoms in mirror cavities interact with photons of light. With superconducting circuits, or circuit QED, we simulate these same dynamics, but using nonlinear circuits. So superconducting circuits are categorized as macroscopic quantum systems, and they have two main properties. One is superconductivity in the name, where you have frictionless electrical current flow at cryogenic temperatures. These temperatures are usually on the order of like 2 Kelvin or below, so really, really cold. And then they also exhibit the Josephson effect, which is where you see circuit nonlinearity. So these are two examples of some very colloquially used like superconducting circuits. The first one is a harmonic oscillator, which is just a inductor in parallel with a capacitor. And then the one on the right for y'all is the anharmonic oscillator, which is the colloquial way that we make a qubit. This is one of the most famous qubits. I'm not going to get into that, but these are just some examples of some superconducting circuits. Yeah, so if we want to couple magnons and photons, or magnons and superconducting circuits, then we kind of need to use a Hamiltonian to describe the total energy of the system. And so we are coupling a macro spin to an LC resonator through some oscillating magnetic field. So we have three Hamiltonian terms. The first one, which is these two terms right here, describes the internal energy of the LC resonator, which you can see is quantized into your current and your voltage that you apply. And then we have our second term is our magnon internal energy, which is described by this like term right here, where B external is the external magnetic field that you apply. And then this last term is our interaction term between our magnon and our superconducting circuit, which is given by this factor right here. This is a very simple Hamiltonian to just kind of describe how you go about writing these systems. So this one specifically neglects magnetic anisotropy. And just as a note, this BRF is a quantized magnetic field that depends on your unit of inductor current for each macro spin in your magnon. So in practice, we take this Hamiltonian and we kind of do the rotating wave approximation, where you flip it into a form where your Hamiltonian is in the frame of the magnon precession. So then all of your dynamics are kind of described from the point of view of the magnon. Yeah, so I guess this is kind of like the first implementation I wanted to show. So this was done by a team at Argonne National Lab in 2018. And so what they did is they started with a niobium superconducting resonator, and then they put a permalloy thin film magnetic device on top, in the center of this superconducting resonator. It's boxed in red in figure A. And then you can kind of describe so the hysteresis for the photon system with these kind of, you see the two modes and the two peaks, and then the magnon system separately has this resonance, or you see your two kind of lines in your two different modes. In this paper, they initially wanted to use thorium iron garnet. I've been calling it YIG. I don't know if it's called YIG in the field. It's called YIG. I love that. But they ran into trouble using YIG because of like fabrication and like deposition. Yeah. So here's kind of how they were like hybridized their magnon photon modes. So this is what the resonator looked like before they added the pi film on top. And then once they added the pi film on top, the resonance started to exhibit extreme anti-crossings, which kind of indicates the high coupling between the magnon and the photon. And then here they give the resonant, like the frequency of the magnon photon system, and then also like the alignment of the system. I want to point out that this resonance at 5, and you can kind of see that 4.8 right here is just from other like modes in the superconducting resonator. So it has nothing to do with the magnon. The magnon is kind of like that sharp one right there. The red line is the curve of best fit for the hybrid mode, and then the blue line in this graph is also the curve of best fit for those relations as well. And so then in 2022, they actually revised this design with using YIG spheres. So this is kind of, they did it in an interesting way. They started with a silicon substrate, they patterned on their resonators, and then they lithographically marked the areas where they wanted to put the little magnet spheres. And then later, after they had finished like fabricating the chip, they then glued in those spheres using a varnish and then let the varnish evaporate out, which is interesting. And so this is like kind of the first design where they exhibited the same like coupling a magnon to like a resonator. This is an optical image of it, and this kind of shows the resonance. This anti-crossing here again shows like the high coupling with the YIG and the resonator. I mean, interestingly enough, with magnon cavity systems, they usually couple on the order of 1 to 3 megahertz, and they were able to, this showed like 38 megahertz, which is a whole order of magnitude like higher than what people have been showing for coupling. So that was really cool. Yeah. And so they then used this same architecture to develop a scheme where they had like 2 remote magnons, and then they coupled those 2 remote magnons together, like through an assisted like superconducting resonator. So if they drive the system with 1 current, by the way, they're driving the current with this, it's kind of small in the diagram, I didn't point it out earlier. They drive it with 1 current, they excite or they couple the photon to just one of the magnons. But if they drive it with a different current, then they're able to like couple the artificial photon to both of the magnons. So they showed like the magnon coupling there. And then they also did like another architecture to show like level repulsion and level attraction with non-Hermitian physics, but like I don't understand it well enough, so we're not going to go into that. It's just also in the paper. Yeah. So a little bit about like the future direction. So magnon and photon hybrid systems are really cool because you can realize circuit quantum electrodynamics and magnetic devices with like on-chip designs. So you can make like on-chip architectures. This is really cool for quantum computing purposes, which like how do you couple quantum systems to like other systems to like make like useful on-chip designs. And then apparently it's also interesting in the context of spintronics, but I don't understand that enough, so I can't talk about it. And then the paper also mentioned like this network being used for scalable hybrid magnetic networks, and then maybe using the silicon-based circuit to like further incorporate photonics. But, like people say this about all quantum computing papers, so like just take that with a grain of salt. Yeah, I still like the device exhibited some really interesting physics, and hopefully they'll be able to do something with that later. But yeah, that's all I have. Thank you.